Hi everybody, welcome to my presentation on extension of range of ammeter and voltmeters, and also we are going to see some solved problems on the same. My name is Swati Polasa, lecturer in Electrical and Electronics Engineering, Sanjay Gandhi Government Polytechnic, Adilabad. You can see in my first PPT, we have an ammeter here, and there are different terminals here. Similarly, we have an voltmeter with different terminals instead of two. And here it is clearly visible that it states 3, here it states 10, here 15. You can see different ranges on the scale. It's from 0 to 10, 0 to 3, and 0 to 15. How it was possible that we could increase the range of the voltmeter from 3 to 10 and to 15. And similarly here we have ammeter readings. I think it's not that clear, but it is trying to show us from around 2.5 amperes and 5 amperes. Getting inside the presentation, the prerequisites of the presentation is we should be aware of construction and working of MC and MI instruments. Assuming that you are aware of it, let us get inside the presentation. So how to use 1 meter for different ranges? How can we measure different currents with single ammeter, and how can we measure different voltages with single voltmeter? To measure different currents with single ammeter, we would be requiring a shunt. So shunt is required, and to measure different voltages with single voltmeter, we require multiplier. We are going to see what is a shunt and what is a multiplier in further slides. So we can also provide this facility by using an auto transformer. So auto transformer can step down the voltage. So we can use auto transformer along with the voltmeter and measure different voltages. Similarly, a rheostat can do the job. We can also have current transformers. Current transformers can step down or step up the currents, and then we can send it to measurement using the available range ammeter. And similarly, we can make use of a rheostat to step down the voltage and then measure the voltages. Let us see. As we have discussed, the shunt is required to extend the range of an ammeter. What is a shunt? A shunt is a low resistance conductor connected in parallel with ammeter to extend its range. So it is a low resistance connected in parallel to extend the range of an ammeter. Let us see how it does that job. This is a circuit diagram which clearly shows how a shunt should be connected. Here you can see generally an ammeter is connected in series with the load. Because we want to measure the current through the load, if we connect the ammeter in series, we can have same current flowing through the ammeter, and hence we can measure the current flowing through the load. So in order to extend the MC ammeter range, here we are taking an MC ammeter range because MC, moving coil, especially permanent magnet, is used to measure DC currents. So here we are looking into that case of extension of MC ammeter range using shunt. So this is ammeter. In parallel with the ammeter, we are placing a low resistance RSH. Let us see what happens. We are trying to measure current I because I is the load current and IM is the meter current. Current that passing through the meter is IM. Current flowing through the shunt resistance is ISH. And of course, when you connect load here, same current I flows through the load. So with reference to the same figure here, let Rm, the internal resistance of the coil in ohms, RSH, the shunt resistance in ohms, Im is the full scale deflection current in ampere. Full scale deflection means when Im current flows through the through the ammeter, the pointer will give full scale deflection. It will indicate full scale value. And ISH is shunt current in amperes. I is current to be measured in amperes. As we have seen, I is the current flowing. So there is a split of this I. Large amounts of current will flow through ISH because shunt resistance is very less value resistance compared to the meter. And here we have again ISH, IM adding at this junction and I, which is equals to IM plus ISH, will flow through the load. So here you will be having load. Hope you are clear with this. So since the two resistances are in parallel, voltages will be same. So ISH RSH is equals to IM RM. So IM this is our meter and meter resistance is RM. We had a shunt here. Shunt resistance is RSH. Here the current flowing is IM and here the current flowing is ISH. The voltage across the meter is IM into RM. This is our VM. Voltage across the shunt, say it is VSH, it is equals to ISH into RSH. Because the meter and the shunt both are connected in parallel, VM is equals to VSH. So VM is equals to VSH. It will be concluding that VM is IM into RM is equals to ISH into RSH. So RSH from this is equals to IM RM by ISH. According to the Kirchhoff's current law, here we have I current, that is the load current. So if you write Kirchhoff's current law at this junction, we will get I is equals to IM plus ISH. So from this, it means sum of currents entering is equals to sum of currents leaving. Currents leaving this junction are IM and ISH, and there is only one current that is entering into the junction, which is I. Hence, I is equals to Im plus ISH. From this, we can write ISH is equals to I minus Im. Now, we know ISH. So, here, from the formula that we got here, RSH is equals to IMRM by ISH. In this ISH, I am going to replace it by I minus Im. So, I'll be coming up to the equation saying RSH is equals to IMRM by, instead of ISH, I am writing I minus Im. Dividing both the numerator and denominator by Im, if I divide both the sides by Im, here Im will get cancelled and here I'll be getting RSH by Im. So we had RSH is equals to RSH is equals to IMRM. Let me write it here. RSH is equals to IMRM by I minus Im. Now, by dividing Im on both the sides, I'll be left out here RSH on, Im on both numerator and denominator. Here, that means this is the numerator by Im and denominator here also by Im. So Im will get cancelled out. This Im will get cancelled out. If I take this, distribute this Im inside, I'll be left out with Im by I by Im minus Im by Im. Numerator, I'll have Rm. Denominator, I'll have I by Im minus Im by Im. So here, Im and Im gets cancelled and I'll be left out with only one. Hence, we get this equation that RSH is equals to Rn by I by Im minus 1. So here, instead of I by Im, I am replacing it with a variable M. So I'll get RSH is equals to Rm by M minus 1. Here, M is called as multiplication factor of shunt. So how did we get M? It is I by Im. What is I? I is current flowing through the load which you want to measure. And what is Im? The actual current flowing through the meter which is trying to measure the load current. So here I by Im is again given by 1 plus Rm by RSH. It is simply by simplifying. So you have this equation that is pointed. RSH is equals to Rm by M minus 1. Here, in this, if we solve for M, we will get M is equals to 1 plus Rm by Rsh. We will do it quickly. So here Rsh is equals to Rm by M minus 1. I'll take this M minus 1 to other side and Rsh to this side. So I'll get M minus 1 is equals to Rm by Rsh. So M is equals to, I'll take 1 to other side of the equation. So 1 plus Rm by Rsh. Thus, we can extend the range of MC ammeter as shown in earlier. Now, let us see for AC measurements how to extend the range of MI ammeters. Now, when MI comes, inductance of the coil comes into picture. Why? Because AC currents are flowing through the meter. So, when AC currents are flowing through the meter, instead of just mentioning the resistance of the meter, we are also mentioning the inductance of the meter. So, Lm is the inductance of the meter. Now, here, while placing the shunt here, it is a coil. So, I will have resistance of the shunt coil and inductance of the shunt coil taking into picture. Why again? Because we are trying to measure AC currents. Here our I is AC quantity. So there is a split in currents, IM and ISH. ISH will be more because RSH and is the resistance of this is going to be small. And we have again I flowing into the load. Let Rm be the internal resistance of the coil, RSH shunt resistance, Im full scale deflection in current in amperes, ISH shunt current in amperes, and I be the current to be measured in amperes. Ln is the inductance of the instrument in Henry, LSH is inductance of shunt in Henry, and time constant of instrument. Time constant of the coil is L by R. So the time constant of the instrument is Lm by Rm. Similarly, time constant of shunt is LSH by RSH. Now, if you want your MI instrument to be accurate, so for accuracy, we should take care that the time constant of shunt coil and the instrument must be equal. That means Ln by Rm should be equals to LSH by RSH. Say it is equals to some K value because both are same. We will, in case if we get Ln by Rm or LSH by RSH in our equation, we will simply replace it by K for convenience. So when it is equals to K, Lm should be equals to K times of Rm and LSH should be equals to K times of RSH. Now the ratio of currents is inversely proportionate to their impedance. ISH, because we know that current is inversely proportional to impedances. So ISH by Zm is equals to Zm by Zs. So Z is the impedance, Zs is the impedance of the shunt, Zm is the impedance of the meter. So Z is equals to root over resistance square plus reactance square. So here we have inductor. So reactance of inductance here. So R square, which is Rm square plus omega. Let omega be the frequency angle. Okay. 2 pi f. So 2 pi f, their f value is the frequency of the current that we are trying to measure. Omega into Ln whole square divided by Zs value is root over Rsh square plus omega Lsh whole square. This is the reactance of the shunt. This is the reactance of the meter. So here we will just replace Ln by K times of Rn, Lsh by K times of Rsh. Hence, our next step will be this. Here, Rn is common in the numerator on both the terms inside the root. So if I bring it outside, I'll get Rn square. I can bring that Rn square outside the square root. Then I'll be left out with Rn. Let me simplify it. So here numerator, I have Rn square common. In this term, I'll be left out with 1. Again, I have plus. In this term, I'll be left out with omega square. K Rn square is K square Rn square. So I'll be having K square. Rn square is taken outside. And here, Rsh square is taken outside. From this term, I'll be left out with 1 plus omega square and K square is left. Rsh is anyways taken outside. Now 1 plus omega square K square I have into Rn square. I can take root over Rn square, which is Rn, by root over Rsh square. I'll be left out with Rsh. Here numerator, I'll be left out with 1 plus omega square K square divided by root over 1 plus omega square K square. Because they are same, they get cancelled out, and hence I'll be left out with Rn by Rsh. So coming to the extension again, we have ISH plus IM by IM is equals to Rn plus RSH by RSH. Just like the step that we made in MC, we are just directly writing that equation. See here. See here. We have written same thing, we are trying to write it here. So ISH, I'll just write it. We know that the shunt and meter both are connected in parallel. So we can write ISH plus IM by IM is equals to RM plus RSH by RSH. Now from that, I by IM is equals to RM plus RSH by RSH. I by IM is what we term as multiplication factor m. RSH is equals to Rm by m minus 1. This we know it already. So the one thing we have to observe is in MC we have taken only resistance into consideration, whereas for MI we take both resistance and inductance into consideration. But here we have ISH by IM is equals to Rn by RSH when the time constant of meter is same as time constant of shunt. Now here we can write same thing that ISH by IM is equals to Rm by RSH. If you add both the sides with 1, we'll get this thing. Okay. Again, we got RSH is equals to Rm by m minus 1. So, this is an important point to be noted for MC because we are measuring only DC. Only resistance will come into picture. For MI, both R and L will come into picture. Extension of MC ammeter range. Let us see problem on extension of MC ammeter range. A 1 milliampere moving coil instrument with an internal resistance of 100 ohms is to be converted into 100 milliampere meter. Calculate the shunt resistance required. So the meter current should be 1 milliampere. Then if you see the same thing, let me go to the question again. 1 MA moving coil instrument. So if you give 1 milliampere, it will have full scale deflection. So it's IM is equals to 1 milliampere. RM is given as 100 ohms. And we have to find out the shunt resistance when I is equals to 100 milliamps. 100 milliamperes is I, so we'll do the same. What is the multiplication factor? It's I by IN, which is 100 by 1, that is 100. And RSH formula is Rm by n minus 1. We know Rm 100 by 100 minus 1 is 100 by 99. And 100 by 99 will result to 1.01 ohms. Let me draw the circuit. This is our I, which is 100 milliamperes. There is our meter. It shows full scale deflection from 1 milliamperes and its resistance is 100 ohms. Now we are trying to connect a shunt coil here again 100 milliamperes. So what should be the shunt value in order that when 100 milliamperes current flows, the meter should show full scale deflection. That will happen when RSH is equal to 1.01 ohms. If you compare the resistance of the shunt with the resistance of the meter, it is very, very, very small. We'll just quickly summarize what we have learned about shunt. Shunt is used to extend the range of an ammeter. The multiplication factor of shunt M is equals to I by Im. Shunt resistance RSH formula would be Rm by M minus 1. And we have solved a problem using the formula. Now let us understand how to extend the range of voltmeter. For that, we have seen that multiplier will help, and let us know what is a multiplier. Multiplier is a high resistance element connected in series with the voltmeter to extend its range. If we just try to recollect, a shunt was a low resistance conductor element connected in parallel with the ammeter to extend its range, whereas a multiplier, quite opposite to shunt, it is a high resistance element. Connection is also opposite. It should be connected in series with the voltmeter to extend its range. Now, the properties required for a multiplier is it should have low temperature coefficient of resistance, and the resistance should not change with respect to time, and they should have negligible inductance. Now, this is the circuit, how we connect a multiplier. So, this is a supply voltage which is given to load, and we want to measure this load voltage. To measure the load voltage, we know that we have to connect a voltmeter parallel to the load. 2 bullet points we have to remember. An ammeter should be connected in series, because when it is connected in series, current through the load will be seen as the current through ammeter, and hence ammeter will be indicating current through the load. Similarly, a voltmeter should measure the voltage of the load, and hence it should be connected in parallel to the load, because parallel circuits will be having same voltage. Now, this is our voltmeter. It should be connected in parallel to the load. But the load voltage is out of range of the voltmeter. Hence, we are trying to extend the range of the voltmeter. For that, we are including a resistance, high resistance, in series with the voltmeter. Now, our meter is this whole setup. It is not just this one, it is the whole setup. And this setup is having a voltmeter in series with a multiplier. This RS, a series resistance, is what we call as a multiplier. If we check out the current parameters, the meter current is Im, and Rm is the meter resistance. Rs is the series resistance of a multiplier. So let Rm, we have discussed all these. Im is the full scale deflection current in the amperes, and the voltage of this circuit should to be measured is in volts, that is V. You can see the same. Now V is this. This should be V. This value should be V. Is shown here. Now Im into Rm is the voltage of the meter, and hence it is V, small v actually. For convenience, I'll draw the circuit again. I'll just draw the load side. This is the load. And we want to measure the load voltage, say it is V. I'm having series resistance and I'm having meter, MC meter here. The current through MC meter is IM. Voltage across MC meter will be IM into RM because RM is the resistance of the meter. Now, same IM current flows through the series resistance also. The voltage across the load is same as voltage across this whole setup. So that is what we are trying to write here. V is equals to IM into RM plus IM into RS. Now, from this, IM into RS is equals to V minus IM into R. From this, RS is equals to, I bring IM to this side of the equation. I will distribute IM also, then I'll be left out with V by IM minus IM by IM. IM will get cancelled, so I'll be left out only with RM. I'll show the simplification here. I'll get RS is equals to V by IM minus, I had RM in the previous step by IM. So this IM gets cancelled. So I'll be left out only with RM. Small v, as we have discussed, small v is the voltage drop across the meter. So this is the voltage drop across the meter, and this should be equals to small v. Multiplying factor M is equals to V by V. What is capital V? It is the voltage to be measured, capital V. Small v is the voltage across the meter. So M multiplication factor is equals to IM into RM plus RS, that is capital V, and small v is IM into RM. From this, I'll get M is equals to 1 plus RS by RM, simplifying the problem. In this, if I solve for RS, the multiplied resistance or the series resistance is equals to M minus 1 into RM. Take 1 to other side, also take RM to other side. We will be coming up to this value. Coming to the extension of a range of MI voltmeters. For MI voltmeters, again, as we have already discussed that the inductance of the multiplier should be negligible. We are not drawing or showing inductance of multiplier, unlike the shunt for extension of ammeters. So here I'm not showing LS because it is very negligible. I'll take it as 0. And here I have LM and RM. Why I have to show L? Because we are trying to measure AC quantities. Hence, inductor will come into picture. So with reference to the picture, here figure, Rm, resistance of the meter, Lm, inductance of the meter, Im, current through the meter, omega, angular frequency, small v, voltage drop across the meter. Then we have voltage across the meter is voltage across inductance and across resistance. If we just write here, small v would be current into impedance of the meter, which is, the current is Im into impedance Rm plus j omega Lm. Coming to the magnitude of V, I'll get magnitude means square root of real part square plus imaginary part square. So it is Im Rm square plus Im omega Lm square. Now Im square is common. I will bring it outside the square root. I will be left out of it. Im into square root of Rm square plus omega Lm whole square, and that is written here. Now the total impedance of the circuit would be, instead of Rm, it includes Rs also. So Rm plus Rs whole square plus omega square Lm square. Circuit impedance, I will draw circuit for convenience. This is the load and this is my Rs, and instead of meter, I will draw it as Rm and Lm. So the total impedance Z of the meter is Rs plus Rm plus J Lm. Magnitude is shown here. The meter current would be total voltage by total impedance. So total voltage is voltage across the load, which is capital V. So V by Z would be our meter current. So the total voltage is equals to meter current into root over total impedance. So this is how we get the voltage. And we know the multiplication factor M is capital V by small v. So capital V, we got it as Im times of. So we actually had capital V value as Im into total impedance. This one, capital V. This is capital V. So this is Im into Z. So Z value magnitude is root over Rm plus Rs whole square plus omega Lm whole square. Now small v is meter voltage, voltage across the meter. Meter impedance is Rm plus J. I'll write Zm here again. It is Rm plus J omega Lm. So its magnitude is this one. Again, we have same current flowing, so it I am gets cancelled, hence we will be left out only with this equation. So M is given by the expression of this. We'll see a problem. A moving coil instrument having a coil resistance of 2 ohms gives full-scale deflection when a current of 50 milliamperes flow through it or pass through it. Calculate value of multiplier so that the meter can be measured voltage of 500 volts. So these are given things. I will show everything in drawing. We have shunt resistance and we have a meter. So this series resistance value is not known. This is RS. Current through the meter is known, which is 0.05 amperes. Meter resistance is 2 ohms. And the total voltage that you want to measure is 500. If you take meter as it is, the meter can measure voltage of small v, which is Im into Rm, and that is 2 into 0.5, 0.05, which is 0.1 volt. And we want to extend the range of this 0.1 volt to 500 volts. So please understand how much we are trying to increase the range of the meter from 0.1 to 500. Now we simply use the formula directly here. RS is equals to, the formula is RS series resistance is equals to V by V, which is V by I. Capital V, which is the voltage we want to measure, by Im, current through the meter, minus Rm, meter resistance. So we use the formula V, which is 500, by Im, which is 0.05, minus Rm, which is 2. Hence we get the value of 9,998. 500 divided by 0.05 will give you 10,000. 10,000 minus 2 is 9,998 ohms. If you compare the resistance of the series, that is a multiplier, and resistance of the meter, so multiplier resistance is very, very high compared to the meter resistance. Let us summarize. Multiplier Multiplier is a high resistance connected in series with the voltmeter to extend its range. And the multiplier resistance Rs is equals to M minus 1 times of Rn. We can use this same formula in the earlier problem also. We can use 3 by Im minus Rn. Why? Because M times of Rm is V by I. Okay. Before going into further problems, let us just try to understand about furthermore about a shunt and a multiplier. As we have seen that shunt inductance cannot be ignored when we use it for AC measurement. And also we have seen that shunt resistance is very, very small. So the construction of shunt would be like this. Shunt is made up of a conductor with more thickness. It is made up of a material with whose thickness is more. So at the coil thickness of the shunt coil is more in order to reduce the resistance. So the cross section of the wire is more. So and also the coil thickness will be more because we have to have a good amount of resistance, number of turns would be more. And coming to the multiplier inductance should be very, very less or almost negligible. So we should be having a high resistance. So the multiplier will be having very thin cross-section area. So multiplier or a series resistance will be very thin. If you look inside the meter, the multiplier will be very, very thin and with less number of turns. So now, listening to that, let us get into the problems. There is a one problem. It says that a moving coil instrument has 1 ohm resistance and gives full scale deflection when current is 100 milliamperes flows through it. Now, if resistance of 9,999 ohms is connected in series to the moving coil, up to what voltage can instrument be used? So we want to know how much voltage the measuring instrument can be used. Here we have shown 500. It is actually not known. We have to find out. So let us get into the solution. We'll just list out what are given things here. So RSE, this value is 9,999. RM is 1 ohm and I is 0.1. This is our load. We want to see what is the V value meter can measure. So V value is, this is the V value, voltage from here to here. It is meter current into series resistance plus meter resistance. So Im into RAC plus Rm. Im value is 0.1 into RAC is 9,999 plus 1. So this comes up to 10,000 into 0.1. So our new voltage value, which our meter should be measuring, should be able to measure is 1000 volts. Actually, if you use meter as it is, it should be able to measure voltage up to Im into Rm, that is 1 into 0.1, which is 0.1 volt. But it is made with the help of multiplier and it is made to measure voltage of 1000 volts. Let us see another problem. A moving coil instrument gives a full-scale deflection for current of 20 milliampere with a potential difference of 200 millivolt across it. So they have given a meter. I'll just draw the meter. Here I'm having a meter and the meter current is 20 milliampere for full scale deflection and the voltage across the meter is 200 millivolt. So obviously the resistance of the meter Rm should be equals to V by I, that means 200 millivolt by 200 milliamperes, which is 1 ohm. Calculate shunt required to use it as an ammeter to get a range of 0 to 200 amperes. So this is our meter and we have to use this meter to measure current from 0 to 200 amperes. That means when 200 amperes current flow, the meter pointer should get fully deflected. It should show the maximum full deflection value. But actually our meter is capable of measuring only 20 milliamperes. I have to make this meter now to measure current of 200 amperes. So for that purpose, I have to place a shunt. I have to place a shunt resistance so that it is capable of measuring current of 200 amperes. So this is RSH and Rm is 1 ohm as we have seen. Now we have to calculate. And then what else is asked in the problem? Another one asked in the problem is what calculate multiplier required to use it as a voltmeter of range 500 volts. So in the same problem, we are going to see the same meter. How can you connect it? How can you use it as a voltmeter? And how can you use it as an ammeter? So the above circuit is for the meter to use it as ammeter to measure the range up to 0 to 200 amperes. And now we are going to see the connection for the same meter to act as a voltmeter to work for the ranges from 0 to 500. So this is our meter. We are going to put a series resistance multiplier and Rm is 1 ohm. Current through this branch is 20 milliamperes. Voltage across the meter is 200. So Rm value is 200 millivolt by 20 milliamperes, which is not 1, sorry, it is 10. Here Rm value is 10 ohms. And here the voltage is shown as 200 millivolt. Let us proceed forward. To this we have load connected. This is the load. Well, let us test this out. the given data, convert the values from milliamperes to ampere, millivolt to volt. Meter resistance is Vm by Im. It should be 10 ohms that we have calculated already. Now, if you want it to work as an ammeter, we require a shunt. The load current, we want its full scale deflection at 200 amperes, so 200. Now we just use the formula of shunt resistance, IMRM by I minus Im. So it is going to be 0.2. We know Im 0.2 into 10 by 200 minus 0.2, and it is going to be 0.001 ohm. So RSH value required is 0.001 ohm. We can also use the formula of Rm by M minus 1, where M is equal to I by Im. Hope you've understood. Let us go further. When it is used as a voltmeter, we require a multiplier. This is our meter. We connect it to a multiplier. Given data, the voltage should be measuring 0 to 500 range. We have to find out the multiplier. Formula is V by Im minus Rm. V is the voltage, total voltage it has to measure, which is 500. By meter current is 0.02 minus meter resistance is 10. So the multiplier resistance is 24.99 kilo ohms. Very huge. Please note it down. Hope you're clear with the problem. I'll have a quick recap. We have simply used formulas here, which we have derived earlier. Let us see another problem. Here the problem states that there is a moving coil instrument of resistance 10 ohms. This is also an NC instrument. It gives full scale deflection when it is carrying 50 milliamperes, and show how it can be adopted to measure voltage up to 750, current up to 100 amperes. So it is just the same as the previous one, but the values are different. So current up to 100, voltage up to 750. This is our NC meter. What is given in the meter resistance is 10 ohms. It is given. So Rm is 10 ohms. And current through meter Im is given. Im is 50 milliamperes. Here also the current is 50 milliamperes. Then when 50 milliamperes flows, the meter will show full scale reflection. That means if this is the pointer, pointer will be showing full scale reflection. This is the full scale value. So it is starting from 0 to say some value. Here it is, if you take meter as it is, say some value x. So the pointer will show full scale reflection when the meter carries current of 50 milliamperes. And then we want to use this meter as an ammeter and as a voltmeter. So let us see for voltmeter purpose, and the range is from 0 to 750 volts. So that means capital Z value is 750. Let us get into the solution. It is same as the previous one. So this is the circuit. So Im is equals to 50 milliamperes RMS. Then we want it to measure 750 volts. For that, we have to connect the multiplier. We need to find out how much is RS value. Meter voltage would be Im into Rm. So Im is 50 milliamperes converted to amperes, 0.05 amperes into Rm, which is 10 ohms. So the meter voltage is going to be 0.5 volts. We'll see the same in the figure. So this voltage value is the meter voltage and it is 0.5 volts. Now the supply voltage, it is 750. So we know this formula, Rs is equals to V by Im minus Rm. So V is 750 by Im is 0.05 amperes minus Rm, which is 10 ohms. Hence we get Rs is equals to 14,990 ohms. If you connect a multiplier having resistance 14,990 ohms, then the meter will have full scale deflection for the voltage value 750, which means the meter is ready to measure voltages from 0 to 750. It is direct substitution of the formula. We have to just understand the given data and we should be able to draw a circuit with the given data by our understanding. Let us see the second part. This is our set for the meter to act as an ammeter, which should be able to measure currents from 0 to 100 amperes. Initially, the meter as it is will be able to measure 50 milliamperes. That means by taking 50 milliampere, the pointer will go to full scale deflection. Now we are trying to extend the range, which means when 100 amperes flow into this setup, meter will be having full scale deflection. So for that, we need to find out the shunt resistance. So we have shunt current is equals to input or the load current minus meter current. So it is 100 minus 0.05 amperes. It is going to be 99.95 amperes. So current through this shunt resistance is 99.95 amperes. Now the shunt resistance is equals to voltage across the shunt resistance by current through shunt resistance. Voltage across shunt resistance is same as voltage across the meter. So voltage across the meter is 50 milliampere into 10 ohms. That is Im into Rm. That's what is mentioned in the formula. Im into Rm by Is is the shunt resistance, which is 0.05. 50 milliampere is 0.05 ampere into Rm, which is 10 ohms, divided by Is, shunt resistance, current. Current flowing through the shunt resistance is Is. We got it already as 99.95. Rs is equals to 0.005. Hence, we get the answer. Hope you understood the problems. So, the expected learning outcome from the presentation would be understand how to use an MI instrument or an MC instrument as an ammeter, how to use it as a voltmeter, how to extend the ranges of an ammeter, how to extend the range of a voltmeter, what is the construction of a shunt, and what is the construction of a multiplier, how to use them, and how to calculate the resistance values of shunt or a multiplier when you want the meter to work for a given range. We have seen some problems also relating to the same. Hope you have understood the concept well and you will be able to perform some problem solving on similar lines. Thank you.